This is Smilla, saying goodnight to her pet. They are both going to sleep now, and that means their brains are going to work. Because when mammals sleep, our brains are active, consolidating our memories. If memories are not consolidated, Smilla and her hamster will not recognize each other when they wake up. This is György Buzsáki. He won the Brain Prize in 2011 for his contribution to the discovery of how this memory consolidation works. Dr. Buzsáki is a professor in neuroscience at the New York University School of Medicine. In his laboratories, scientists study how the internal structures of the brains of mammals communicate and how daytime impressions are secured as memories while we are sound asleep. In the late 80s, György Buzsáki discovered an important element of the memory process. It takes place in the middle of the brain, in a worm-like double structure called the hippocampus. Even though this structure looks different from species to species, there is one in every mammal, and it keeps track of our daily memories. When Buzsáki made his discovery, he was listening to neurons firing in the hippocampus of a sleeping rodent.
I was listening to the loudspeaker and how neurons come together and work together very powerfully. That was an astonishing pattern for me. And then I began to explore in depth what this could be.
It had been known for some time that sleep is important for memory, but it was not obvious why. Suddenly it became clear. During sleep, the hippocampus instructs the brain about what to remember, and does so in bursts of time-compressed information of what we learned during daytime, shuffled and played back in fast-forward and fast reverse.
They are replayed, so to speak, again and again and again in small fragments. And this is the fragment that we identified. This is called hippocampal sharp wave ripple. This is a pattern that lasts for about 100 milliseconds or so. You have about 2,000 of those patterns every single night. If I erase those patterns from your brain, you will not remember this interview tomorrow.
With György Buzsáki's discovery, part of the machinery in our memory system had finally been uncovered. Today, the sharp wave ripples are widely acknowledged in neuroscience and a part of the two-stage model of memory. This model explains why we must sleep to remember well, and it predicts that we might one day be able to improve our memories, learn faster, and alleviate the negative effects of brain diseases. So how does this memory consolidation work, and how might it at some point make us learn better and remember more? The answer is in the brain and in the laboratory.
Hi, David.
György.
Are we in the hippocampus yet?
We are.
Humans, rodents, all mammals seem to consolidate memories in the same way. While awake, the brain processes information and stores it transiently in the hippocampus, exactly where Buzsáki made his discovery. And that makes sense, because the hippocampus is now known as the work desk of our memory.
What happens during stage one? You are listening to me, we are having a conversation, and fragments of this conversation are detected and stored transiently, mostly in the hippocampus.
Neural information about sounds, feelings, smells, visions, places, persons, or whatever we experience is stored here during the first part of our two-stage memory. But just like a work desk is limited in size, so is the hippocampus. The brain needs a library for memories, a safe place where it can consolidate important information so we can retrieve it again. Where are the bookshelves in the brain? Right here, in the neocortex. The large areas in the outer brain where the information was originally processed. These are the areas of the brain that receive the nightly flashes of compressed memories. What Buzsáki saw decades ago was the hippocampus writing memories on the neocortex, organizing memories like a librarian, returning books to the shelves after use. This is the second part of the two-stage memory model, and it rounds up the role of the hippocampus in the brain.
The hippocampus is if you want, is an appendage to the large neocortex. Its inputs are coming from the neocortex and its outputs are going back to the neocortex. So this structure cannot do a lot of things. The only thing that can do reasonably well is modify its inputs and organize its inputs. And this is exactly what the hippocampus is about, is organizing the different information that are stored in different parts of the neocortex.
This process of organizing memories goes on night after night, and it turns out if the nightly flashes of information from the hippocampus are disturbed, so are the memories. Memories can be manipulated during sleep.
We can erase memories, we can make memories disappear, we can make memory impairment pretty easily. The interesting thing would be, of course, how to improve them.
This is an important challenge because many diseases like epilepsy or Alzheimer's disease involve disturbances in the communication between the hippocampus and the neocortex. And that creates memory problems, as it happened for Richard Shane, who had epilepsy before he was finally cured with brain surgery.
For 22 years, I had roughly, what I'm aware of, I'm not sure how many I had when I was sleeping, but I had 3,000 seizures.
Could the memories of patients with epilepsy be helped if the communication between the hippocampus and the neocortex is brought back to normal?
Every single animal model of Alzheimer's disease and autism comes with a distorted form of sharp wave ripples. So we know that that pattern is impaired. So now the question is how we can change the balance between the abnormal patterns and the normal good sharp wave ripple patterns. Can we restore them by any means?
Improving the memory process is a huge challenge for neuroscience, but it is one of the promising perspectives of the work in leading laboratories. That one day we might succeed in this challenge. One day it might be possible to secure more people the consolidated memory of a good night's sleep.